In this section, we are going to learn about L'Hopital's rule, which it gives us a method to find limits. So I have the first part of L'Hopital's rule written on the screen. Basically what it says is if you're taking a limit and you have that indeterminate form of 0 over 0, so if you're finding the limit of f over g and f is 0 and g is 0, then you can take the derivative of the top and the bottom and find the limit of f prime over g prime, and that will give you the answer. So that's what L'Hopital's rule says. L'Hopital's rule also works if you're taking the limit and you get the other indeterminate form, that infinity over infinity. So if you're taking the limit of f over g and f goes to infinity and g goes to infinity, whether it's positive or negative infinity, then that limit will equal the limit of f prime over g prime. So again, you can take the derivative of the top and the derivative of the bottom and then find the limit of that new ratio. So let's just see how this works by doing a couple of examples. So we're going to use L'Hopital's rule to find the following limits. And so let's start with part A. We want to find the limit as x goes to 2 of x squared minus 4 over x minus 2. Now there's more than one way to do this problem, but I want to show you this problem with L'Hopital's rule. So the very first thing I'm going to do is plug the 2 in. I want to see if I get an indeterminate case, because L'Hopital's rule only works when you get 0 over 0 or infinity over infinity. And so if I plug the 2 in for x, I get 2 squared minus 4, so 0 on the top, and then 2 minus 2, so 0 on the bottom. This is indeterminate. That means I can use L'Hopital's rule. And so L'Hopital's rule says take the derivative of the top and the bottom separately. And so the derivative of x squared minus 4 is 2x. And then the derivative of x minus 2 is 1. So L'Hopital's rule says this is going to be equal to the limit as x goes to 2 of 2x over 1. And so once again, I plug the 2 in, see what I get. And this time I actually get a number. 2 times 2 is 4. And that's my final answer. This limit equals 4. Now, since I'm not actually going to prove L'Hopital's rule for you, let me just show you that we can get the exact same answer using that older method that we learned at the very beginning of the semester. So in this particular case, we could have actually found this limit by factoring and simplifying. The x squared minus 4 is a difference of perfect squares, so you could have factored that as x plus 2, x minus 2. And then the x minus 2's cancel out, and you're left with the limit as x goes to 2 of x plus 2. Plug the 2 in, and you get the exact same answer of 4. So there's two different ways we could use to solve this problem. All right, let's do some more examples. Example B, limit as x goes to 0 of sine of 4x over x. So if we plug the 0 in, we get sine of 0, which is 0 over 0. So we get that indeterminate form again. So L'Hopital's rule says I can find the derivative of the top, derivative of sine of 4x. I'm going to have to use my chain rule on that one. Sine is my outside function, so derivative of sine is cosine. I get cosine of 4x. And then I have to multiply by the derivative of the inside. Inside is 4x, so we have to multiply by 4. And then on the bottom we have an x. Derivative of x is 1. So now we're finding limit as x goes to 0 of cosine of 4x times 4. Plug the 0 in. I get cosine of 0 times 4. And then let's see, cosine of 0, that's 1. So 1 times 4 is 4. Here's another one. Limit as x goes to infinity of e to the 1 over x minus 1. all over 1 over x. If I plug the infinity in, I get e to the 1 over infinity minus 1 over 1 over infinity. And recall from a couple of sections ago, when we have a finite number, like 1 over infinity, that's always going to go to 0. And so this becomes e to the 0 minus 1 over 0. E to the 0 is 1, so the numerator is 1 minus 1 or 0. And once again, I get that indeterminate form, 0 over 0. So let's use L'Hopital's rule. So we take the derivative of the top, and I'm going to have to use the chain rule for that. I have e to a power, so I get e to a power, so we get e to the 1 over x, and then we have to multiply by the derivative of the inside function, and this time the inside function is that 1 over x. Okay, so my outside derivative was e to the 1 over x, and then the derivative of 1 over x is negative 1 over x squared. If that's not clear how I got that, I thought of the 1 over x as an x to the negative 1, and then I brought the negative 1 down. I got negative x to the negative 2, so that's where that negative 1 over x squared came from. All right, so that's my derivative of the top, and then derivative of the bottom. Derivative of 1 over x is negative 1 over x squared for the exact same reason I just described. 1 over x is x to the negative 1. We bring the negative 1 down, we get negative 1 x to the negative 2. Okay, so I've used L'Hopital's rule. I found the derivative of the top and the derivative of the bottom. And so now, we can actually simplify this. We can cancel that common factor of negative 1 over x squared out of the top and the bottom. And I'm left with a limit as x goes to infinity, e to the 1 over x. Plug the infinity in. We get e to the 1 over infinity. That's e to the 0 or 1. So this limit becomes 1. Now, so far we've just focused on the indeterminate forms of 0 over 0 and infinity over infinity. And that's important because those are the two cases where you can use L'Hopital's rule. However, there's other indeterminate forms, and we're going to see how we can manipulate these problems so that we can use L'Hopital's rule. So I have listed on the screen 5 other indeterminate forms. So 0 times infinity, infinity minus infinity, 1 to the infinity, infinity to the 0, and 0 to the 0. The first two, 0 times infinity, infinity minus infinity, what we're going to do is we're going to try to rewrite these problems as a quotient or a fraction, because then we'll be able to use L'Hopital's rule. L'Hopital's rule only works when we have those fractions 0 over 0 or infinity over infinity. The ones that have exponents in them, the bottom 3, our strategy is going to involve taking the natural log of both sides, and I'll explain that in more detail when I get to an example. So let's start by trying to find the following limits. Example A, let's find the limit as x goes to 0 from the right of x times ln x. Now that little plus sign, the from the right, doesn't really change how we do the problem. That's in there because when you have a natural log, you can't approach 0 from the left. It's not in the domain, so that's why I put that into the problem. But when you're finding the left and the right limits, it doesn't really change how you do anything. You can still use L'Hopital's rule in the same process. Okay, so the first thing I'm going to do is plug in the 0. And so I get 0 times ln 0. Natural log of 0 is technically undefined. However, if you remember, perhaps look at the graph of the natural log function. At x equals 0, there's actually an asymptote. The graph is going down forever. And so natural log of 0, we're going to say, approaches negative infinity. And so we end up getting that indeterminate case 0 times infinity. Anytime we get that indeterminate case that's a product, we're going to rewrite this as a quotient so that we can use L'Hopital's rule. And so just in general, if you have the product A times B, you can always write that as A divided by 1 over B. Remembering that when you divide fractions, you copy dot flip. This will give you A times B. Or you can write it as B over 1 over A. So it's kind of a general rule if you want to write a product as a quotient. So x times ln x, I'm going to try writing this as ln x over 1 over x. That's the exact same thing. And let's see what happens when we plug in the 0. So now we get ln 0, which we just learned goes to negative infinity. And then on the bottom we get 1 over 0, which is going to go to infinity. So this is still indeterminate. This is an infinity over infinity. And that's a good thing because that means we can use L'Hopital's rule. So the top is ln x. The derivative of ln x is 1 over x. And then on the bottom I have a 1 over x. And the derivative of that is negative 1 over x squared. Again, we explained that earlier. The 1 over x is the x to the negative 1. All right, now I'm going to see if I can simplify this. So we've got 1 over x divided by negative 1 over x squared. Copy dot flip, that becomes limit x goes to 0 of 1 over x times x squared over 1. I'm sorry, x squared over negative 1. And then we can actually cancel an x out of the top and the bottom, and I'm left with limit as x goes to 0 from the right of negative x. So I was actually able to simplify this all the way down to negative x. We're still approaching 0 from the right. So finally, I'm going to plug the 0 in. Well, negative 0 is still 0. And that's my final answer. This limit goes to 0. Okay, let's see what happens when we take a difference. So let's find the limit as x goes to 0 of 1 over x minus cosecant of x. So plug the 0 in. I get 1 over 0 minus cosecant of 0. So it's 1 over 0 minus cosecant is the reciprocal of sine. So 1 over 0 minus 1 over sine of 0. I end up getting infinity minus infinity because sine of 0 is 0. So I basically have a 1 over 0 minus a 1 over 0. And so infinity minus infinity is actually indeterminate. You can think of it as we don't know which infinity is bigger, if that makes any sense. And so this is indeterminate. We really want to try to use L'Hopital's rule. But L'Hopital's rule only works when you have quotients. And so our strategy is going to be, let's see if we can do the subtraction and write this as a single fraction. So what we really have here is a 1 over x minus 1 over sine x. Let's get a common denominator. So we'll take the 1 over x, we'll multiply it by sine x over sine x. And we'll take the 1 over sine x, multiply that by x over x. So now we are left with limit as x goes to 0 of sine x minus x over x sine x. Let's plug in the 0 and make sure this is indeterminate. Sine of 0 minus 0, yeah, that's 0. And 0 times sine of 0 is also 0. So yes, this is that indeterminate 0 over 0. That's good, because that means we can use L'Hopital's rule. So the derivative of sine x minus x becomes a cosine x minus 1. And then to find the derivative of the denominator, the x sine x, we're going to have to use the product rule. I'll let f equal x, and g is sine x, so f prime is 1, and g prime is cosine x. So then we take f prime times g, so 1 times sine x, plus g prime times f, so plus x cosine x. All right, so we took the derivative of the top and the bottom. Let's plug in x equals 0 and see what we get. So on the top, cosine of 0 minus 1, that's 1 minus 1, or 0. And on the bottom, sine of 0 plus 0 times cosine of 0, that's also 0. So what does this mean? Well, 0 over 0, unfortunately, is still indeterminate. Does that mean we can't solve the problem? No, it just means we have more work to do. And so we can actually keep applying L'Hopital's rule if we have something that's indeterminate. So you can apply L'Hopital's rule as many times as you need to until you no longer have something that's indeterminate. So I'm going to apply L'Hopital's rule a second time. So I'm going to take the derivative of the top. The top is now cosine x minus 1. And so the derivative of cosine x minus 1 is negative sine x. And then I'm going to take the derivative of the bottom. So let's see, derivative of sine x is cosine x. And then we've got this x cosine x. Well, we're going to have to use the product rule on that. F is x, cosine x is g, f prime is 1, g prime is negative sine x. And so then we're going to take f prime times g plus g prime times f, and I added that to my denominator. So now I'm left with limit as x goes to 0 of negative sine x. And if we combine like terms, we end up with a 2 cosine x minus x sine x in the denominator. All right, let's hope this was enough. Let's plug in 0, see what we get. So negative sine of 0, that's 0. 2 cosine of 0, that's 2 times 1 or 2. And then 0 times sine of 0 is 0. So I end up getting 0 divided by 2. That's no longer indeterminate. 0 divided by 2 is just 0. And that's my final answer. So when we have the products and the differences, the goal is to rewrite them as quotients. And then we can use L'Hopital's rule as many times as we need to. Now, what about when we have these exponential functions? I guess technically it's not an exponential function, but a function that has some kind of exponent. So limit as x goes to infinity of x to the 1 over x. If I try plugging the infinity in, I end up getting infinity to the 0. And so I don't know what that is. And so this is the strategy we're going to do. We're going to let y equal the original problem. So y equals limit x goes to infinity, x to the 1 over x. And then we're going to take the natural log of both sides. So we get natural log of y. And we're allowed to put that natural log inside the limit. So limit x goes to infinity, natural log of 1 over x. The reason we want to take the natural log of both sides is we have a property that says we can then take that exponent, that 1 over x, and we can move that in front of the log. That's one of our properties of logs. So now we're left with natural log of y equals limit x goes to infinity, 1 over x times ln x. Or if we multiply straight across, that 1 over x ln x turns it into an ln x over x. We're finding the limit as x goes to infinity, and so ln of infinity is infinity, and so you end up getting infinity over infinity, which is indeterminate. So by using the natural log and then the properties of the natural log, we were able to actually write this as a quotient. We have an ln x over x on the right-hand side, and that is something we can use L'Hopital's rule on. So derivative of the top, derivative of ln x is 1 over x. Derivative of the bottom, derivative of x is 1. So now I'm left with ln y equals limit x goes to infinity of 1 over x. I'm going to plug the infinity in, and I get 1 over infinity, which goes to 0. And so I'm almost done. Notice that on the left side, we still have that ln y. We're actually solving for y. And so what I'm left with on this at this stage is ln y equals 0. And so if ln y equals 0, if we put that in exponential form, we get y equals e to the 0, and e to the 0 is 1. And so that's my final answer. This limit equals 1. Let's do one more with an exponent. I know this method is kind of tricky. It takes some practice. So let's do one more. Let's find the limit as x goes to 0 from the right of cosine of 2x raised to the 1 over x squared. All right. So I'm going to think of this as y equals that limit, because then I can take natural log of both sides. So now I've got natural log of y equals limit x go to 0 from the right of natural log of cosine of 2x to the 1 over x squared. I took natural log of both sides because then we can take that exponent, the 1 over x squared, and we can move it out front. So that's just using my properties of logs. So now on the right-hand side, we've got limit as x goes to 0 from the right of 1 over x squared times natural log of cosine of 2x. Let me rewrite that and give myself a little bit more room. And on that right-hand side, we can multiply straight across, and that gives us limit as x goes to 0 of natural log of cosine of 2x over x squared. Let's plug the 0 in, again on that right-hand side, see what we get. So natural log of cosine of 0 is 1. So natural log of 1, that's equal to 0 over 0 squared, which is 0. So we do get that 0 over 0, that indeterminate form. That means we can use L'Hopital's rule on that right side. So derivative of the top, well, we're going to have to use a lot of chain rule there. We've got natural log, that's my outermost function, of cosine of 2x. So that's going to give me the 1 over cosine of 2x. That's my derivative of the natural log. And then the next function is a cosine. Derivative of cosine is negative sine, so negative sine of 2x. And then finally, inside that is a 2x. Derivative of 2x is 2. And then derivative of the bottom, derivative of x squared is just 2x. All right, I wonder if we can simplify this at all. Not a lot we can do. We could cancel the 2's out. And then on the top, we're left with a negative sine of 2x over cosine of 2x. I think for simplicity, I'm going to write that as a negative tangent of 2x. And then we just have an x on the bottom. So let's plug in the 0. Negative tangent of 0 over 0. Unfortunately, that's 0 over 0. It's still indeterminate. So what does that mean? What do we have to do? That means we have to use L'Hopital's rule again, a second time. So we've got this limit as x goes to 0 from the right of negative tangent of 2x over x. I'm going to take the derivative of the top. I'm going to use the chain rule on that. Derivative of tangent is secant squared. So I'm going to get a negative secant squared of 2x. The inside function is the 2x, so times 2. And then we just have an x on the bottom, and the derivative of x is 1. So let's plug our 0 in, see what we get. Negative secant squared of 0 times 2. That's the same thing as negative 2 over cosine squared of 0. Secant and cosine are reciprocals. Let's see, cosine of 0 is 1. So that's just negative 2. So we're not done. We're almost done. We still, on the left-hand side, have that ln y. So ln y equals negative 2. And then if we put this in exponential form, or if you raise e to both sides, you end up getting y equals e to the negative 2. And that's my final answer. That's what this limit is, e to the negative 2. That was my last example for this section. Let me know if anything is unclear.